what we will be going over in this little short video is what do we do with that signal or that set of resistors that you guys created to equal a certain amount of temperature on your proto boards. We looked at a conversion chart. We saw with an RTD at what degree the sensor itself would be in resistance. That's not a usable signal as far as instrumentation goes. It isn't compatible with everything. There's so many different types of signals on the sensor side that we have to convert that over into a usable signal. So what we do to convert that, or what we have, is commonly called as a transmitter. Transmitter is a generic term for anything on the sensor side of a control loop, whether it be flows, levels, temperatures, pressures, whatever we're actually trying to measure. We call those little converters that take the sensor input, convert it over into a usable signal. We call those transmitters. If you remember on your proto board, one of the sets of resistors had to equal 100 ohms. At 100 ohms with a 100 ohm platinum RTD, that is 0 degrees C. If we had a transmitter that had a range of 0 degrees C to 150 degrees C, the sensor itself at 0 degrees C would be inputting 100 ohms. So what I'm going to do is to illustrate the set of resistors that are on your proto board that would equal 100 ohms, which, as we convert it over into a temperature measurement from that sensor, would be at the lower range of our scale. If this is 0 degrees C to 150 degrees C, we would have to create the resistance at those two different temperatures using those resistors on your proto board. We would also have to have a transmitter, one that converted that resistance into a usable signal that we're going to get to over on the other side. If we look at that transmitter, there's an input side and an output side. On the input side, we have 3 terminals on there, and they're indicated by a little schematic or a little wiring diagram or a little illustration, whatever you want to call it, like this. If you remember when you took your ohm meter and you looked at the 3 leads coming out of the RTD itself, 2 of them had basically 0 resistance. Those 2 are indicated by these 2 right here. They're tied together electrically. This one here represents what this amount of resistance would be. So as we're wiring these sensors or these simulated resistances that the RTD would be into the transmitter, we would have to run 2 sets of clip leads, one to there and one to the same side, because electrically they're the same on this end and they have to be the same over here. And we would run a set of clip leads over to this one. That input, this resistance to those input terminals are simulating this right here, 0 degrees C. Now, that's on the sensor side of this RTD temperature transmitter, resistance is the input, and that's what we're simulating. On the output side, the standard electrical signal for all of instrumentation is 4 to 20 milliamps. Now this is not a self-powered device. There's no batteries on board. There's no power supply that we simply plug in, so we have to use an external power supply. The power supplies that we had gone over and used already in lab are the same ones we're going to use. We'll set the output for 20 volts DC. Now this is very forgiving when we talk about the input power, the input voltage that this will work with. We could use 24 volts, which is more of a standard power out in industry, but it will also work with 20 volts. It will also work with 17 volts. This device regulates the output signal. Now, we could just simply, and remember that we live in a polarity sensitive world, so we have to observe polarity. There is a plus and a minus on this. And the rule of thumb on a power supply coming out of the power supply itself, we have a negative and we have a positive on there, right? Let me find my red pen. Here we go. Negative and positive. Rule of thumb, coming out of the positive or the negative, either one, it doesn't matter. But the first device that we come to in a current loop, and remember a current loop is a series loop, no matter how many components are in it, it's one after another in a straight line. The rule of thumb is you come out of the power supply and go to the same polarity. We have the positive terminal on the power supply going to the positive terminal on the transmitter itself. And we could just go from negative here on the power supply to the negative of the transmitter. But we wouldn't be able to read what the signal is on this transmitter. What's the output? We have to be able to do that. We have to be able to measure this. We don't take anything in instrumentation for granted. We have to measure everything that we do. So you guys are going to use your current meter. Same one we've been using in lab. And to follow the rule of thumb. Coming out of the negative of our power supply, we're going to go to the common of your meter. Now, we don't have much of an option left, do we? The jack where you put your power supply lead into to read current, there's only one open here and one open here, so that must go right there. You have created a current loop. You have created something that goes from positive single line back into the negative, and we have current. And as we've learned that current in a series loop is the same. We didn't have to put our meter down in this fashion. We could have put it in this line over here, and it will read the same current. It'll be the same current no matter where you read it throughout this entire loop. Now, if we create 100 ohms as an input, and that 100 ohms should be 0 degrees C, or that's what it's representing, there should be a standard signal over here, and there is. The standard signal is 4 to 20 milliamps. 4 to 20 milliamps. So if we create that resistance that equals 0 degrees C, and we read the current coming out of here, we should be at 4 degrees. And if we create the resistance that it takes to represent 150 degrees C, we should be reading through this current loop over here 20 milliamps. If we're not, we have to adjust that. There is two adjustments, two small adjustment screws on the transmitter itself. There's a 0